Hello, chemists! This is Ms. Placino, and you're watching lesson 6.7 on empirical and molecular formulas. In this lesson, we're really going to talk about how to determine both empirical and molecular formulas. And it's going to be pretty closely tied to lesson 6.3 when we talked about percent composition by mass. In order to find the empirical formula, we'll use percent composition by mass data, kind of work in the opposite direction. So, goals for today's lesson. Define the terms empirical formula and molecular formula. Determine the empirical formula of a compound using percent composition by mass. And determine the molecular formula of a compound using molar mass. So really, I think that middle one is the most challenging and arguably most important one for today. So let's go ahead and get started. I'm going to talk about combustion analysis for just a moment. Combustion analysis is one way that we can kind of get the percent composition by mass data. So we would take a compound perhaps that we've synthesized that we don't really know exactly what's present in it. And this is one technique we could use to start figuring out the relative percentages of the different elements in the compound. Basically what happens is we're going to take our sample, so whatever compound you've got, you're going to combust it, aka burn it, react it with O2. And as that reaction occurs, we're going to produce some pretty predictable compounds. Usually you're going to be igniting some sort of hydrocarbon, so we'll be able to produce carbon dioxide and water. So we'll have the different kind of like collection apparatuses that this sample will go through after you've lit it on fire, and they're going to absorb water and carbon dioxide in this example in particular, and based on the mass of water absorbed and CO2 absorbed, you can start to work backwards and figure out the percent composition by mass of, in this case, like hydrogen, carbon, and potentially oxygen. So it's not that chemists just sit around and like look at formulas and try to figure out like, okay, what's the percent composition by mass? And oh, can we take that and go in the opposite direction? These are actually techniques that are used to help discern the formula of different chemical compounds. So let's get into some practice problems. We'll start with empirical formulas first. And again, I think these are a little bit more involved and more difficult to come up with. But basically, an empirical formula will provide the ratio of atoms of each element in a compound in lowest terms. We're generally talking about this with covalently bonded molecules. Your ionic compounds, a formula unit is always an empirical formula. So this is, again, mostly covalence. So this C6H12O6, is this an empirical formula? No, of course not. I can take all of those subscripts and divide it by 2. This tiger is correct. The subscripts will reduce. What would be the empirical formula for this is glucose? Yeah, if I divide everything by 6, I should have CH2O. That is an empirical formula as it cannot be reduced down any further. So basically, we're going to find the moles of each element present within the compound, and we're going to use that information to set up this ratio of atoms. Let's try out a practice problem. So I'm going to jump down to the last of the problems, just because I think this one is a good one to kind of illustrate all the things that we should be able to do with empirical molecular formulas. So question 4 is looking at nicotine, and we're told the percent composition by mass of carbon, hydrogen, and nitrogen. We're going to try to find both its empirical and molecular formula. Now, I'm hopeful that from the reading, you kind of got down the procedure on how to do this, and now we can just put it into practice. So I've got carbon. I'll start there first. Percentages aren't particularly helpful for us in chemistry. So we're going to assume we're working with 100 grams of our substance. If I've got 100 grams of a substance and 73.9% of it is carbon, what mass is carbon? No calculator required. We're just going to, kind of change the unit. So I've got 73.9 grams. Everything in chemistry works through the mole. So we've got to get out of grams and into mole. We can use the molar mass for that. 12 grams of carbon will give us 1 mole of carbon. So I can take 73.9 divided by 12 And I'm going to take this out to a bunch of places. I'm not going to really worry about significant figures at this point in time. That's it. This is what we need to repeat for the other two elements in our compound. So if you think you've got it, go ahead, pause me, and take care of this on your own. I'll walk through it again just to make sure. Let's look at hydrogen. I'm going to assume it's 100 grams, so that would give me 8.7 grams of hydrogen. I need to get out of grams and into moles. 1 mole of hydrogen atoms would have a mass of 1 gram. But wait, Ms. Bocino, isn't hydrogen diatomic? Don't I have to? We're not talking about H2. We're just talking about hydrogen. Hydrogen atoms have a mass of 1 gram per mole. Math I can do in my head. 8.7 mole hydrogen. And finally, we've got nitrogen. It's 17.4% by mass, so we'll convert that into grams by assuming 100 grams. 1 mole of nitrogen atoms would have a mass of 14 grams. But nitrogen is diatomic. We just talked about it. We're talking about nitrogen atoms in this case, not nitrogen molecules. Leave it just as 14. So 17.4 divided by 14 gives us 1.24, call it 3 moles nitrogen. Okay. Now, you've probably seen enough chemical formulas by this point in time to know that I can't have subscripts with decimal points, but I need to keep this ratio constant. So in order to do that, I'm going to take all 3 of these mole values for carbon, hydrogen, and nitrogen, and I'm going to divide by the smallest one to set up a 1 to something ratio. 1.243 is the smallest, so I'm going to divide all my numbers by that. Hopefully we end up with something pretty close to whole numbers. 6.158 divided by 1.243. I get 4.95. I feel pretty comfortable calling that 5. 8.7 divided by 1.243. Okay, I get 6.99. Oh yeah, I feel really comfortable calling that 7. So let's kind of write it down. We'll call that 5. That rounds nicely. 7. That rounds nicely. Like just over or just under a whole number, you want to round. If it's like somewhere in the middle, you've got a little bit more work to do. What do these numbers represent? The 1, the 7, and the 5 for nitrogen, hydrogen, and carbon respectively. Yeah, these are the subscripts. So I would have carbon 5, hydrogen 7, nitrogen. That is my empirical formula. As far as the order of the elements, I tend to give them to you in the same order I want them. There are rules for it, but if like you made this like NC5H7, like you misorder them, that's completely fine at this point in the game. So there's my empirical formula for nicotine. Let's go back to the notes and talk about how to get the molecular formula. Finding the molecular formula is not nearly as labor intensive as finding the empirical formula. A molecular formula is going to provide the actual number of atoms of each element in a compound. It might be in Low's terms, more likely it isn't, but those subscripts represent exactly how many atoms would be present in the compound. So caffeine, we see C8H10N4O2. This is definitely a molecular formula. I could go ahead and reduce those. I could cut everything in half to get the empirical formula, but this is telling me how many atoms of carbon, hydrogen, nitrogen, and oxygen are present in caffeine. Reds are the oxygens, you got blue for the nitrogen, black are the carbon, white are the hydrogens. It's telling us exactly what's there. In order to make the leap from empirical to molecular formula, we need a little bit more information. Specifically, we have to know the molar mass of the compound. Without that, you can't really determine the molecular formula. So let's go ahead and finish up our practice problem. Okay, so I've got my empirical formula, and if I look back at the question, I do have information about nicotine's molar mass. Nicotine has a molar mass of 162.3 grams per mole. what I need to do is find the molar mass of my empirical formula. So I've got 5 carbons, 5 times 12, plus 7 times 1 from hydrogen, plus 14 from the nitrogen. And that gives me a molar mass of approximately 81 grams per mole. Now, ideally, a molar mass should be some multiple of your empirical formula mass. So just to kind of really go through the math, 162.3 grams per mole, that's our molecular formula, divided by our empirical formula's molar mass. That's pretty close to 2. What do we do with that number? We're going to take, in this case, 2 and multiply it by each of the subscripts. So I'm still going to have carbon, hydrogen, and nitrogen. 2 times 5 gives me 10. 2 times 7 is 14. And 2 times 1 is 1. So in blue on the screen, C10H14N2 is the molecular formula of nicotine. And notice that you could reduce down those subscripts and get back to the empirical formula if you wanted to. All right, so it's the empirical formula work their students tend to make their mistakes. Really common mistakes include with elements that you know exist as diatomics, counting them as diatomics, using their diatomic mass. We don't do that with empirical and molecular formulas. It's just hydrogen atom, nitrogen atom, oxygen atom. Don't try to represent them as diatomics. Once you've got the moles of each element, we need to set up a ratio, a 1 to something ratio. And the best way to do that is to take your smallest number of moles and then divide all of the numbers of moles by that. You should get pretty close to whole numbers. If you end up in the middle, you got a little bit more work to do. I'll let you figure that one out on your own. But 4.95, 6.99, plenty close enough to whole numbers to round. These numbers become subscripts in the empirical formula. To go from empirical to molecular, I've got to give you the molar mass. There's no way for you to do it without that piece of information. Kind of figure out what factor you're going to have to multiply by, and then multiply the subscripts by that to get the molecular formula. All right, nice job today, chemists. That wraps up the lesson and wraps up Unit 6. Definitely worth going through and doing more practice, get comfortable with these concepts and all of these calculations. Thanks for tuning in, and I hope you found this video helpful.